Hello. Yeah. So good evening, everyone. I'm Vijay. This session, as you all know, is about deep learning. We'll have a basic introduction on deep learning. So let's start. You have the slides and the code file in the YouTube description. So you can follow along the slides if it's not clearly visible. Okay, so let's start. Introduction to deep learning. About me, I'm Vijay Nandwani, and I'll be starting my final year at Srinagar University next month. I'm currently a part of a startup called When You All, and in my free time, I like to read and learn more about latest developments in technology. If you have any queries and you want to connect with me, my email address is contact@vijaynandwani.me, or you can add me on Facebook or LinkedIn as well. So, what is this webinar about? This webinar aims to provide everyone a basic introduction to deep learning. Like if you have just heard the term deep learning, but you really don't know what is it and how to start with it, then this webinar is useful for you. Some programming experience is required to understand, but you really don't need to know all the libraries and all. You just need to know how you program. That's it. We'll cover some theoretical concepts first, and then we'll move to a live demo. This topic is actually vast. It's covered in universities as semester long course. So in next 1 to 1.5 hours, we'll be covering only the basics of deep learning. I'm pretty sure it would give you enough confidence to read more about it on your own. You can explore more topics once you are covered with the basics. And it's all being recorded, so you can watch it again. The slides link is with you, so you can watch the slides again. And after the webinar is over, we'll be circulating a feedback form, so you can fill the feedback form. And this topic is actually is people get scared initially when they start reading about this topic. It's very daunting, and I'm pretty sure when you start and when you later in this webinar, you'll hear some terms and you might get scared. Okay, some mathematics is involved, but trust me, it's all very intuitive. I'll repeat again that it's all very simple. I mean, I am myself not good at mathematics. I have 7 CGPA, and it's not that I'm good at maths. No, but it's once you will get the basics, once you'll get the introduction to basics, you'll realize that these concepts are very intuitive, and you just need to get over the phobia of it. That's it. So lastly, I'm not an expert in this domain. I'm still trying to learn more in this field. So if I make any mistake during the webinar, please let me know in the feedback form or in the comments. I'll have a look at it. Okay, so let's get started. What is deep learning? Today, deep learning is one of the most trending topics in industry. The startups in this domain are raising millions of dollars of funding. And companies are looking for people who know this field, who know this technology. So some people predict that the developments in deep learning and AI are more impactful than the invention of computers or smartphones. The next big thing is going to be in AI, deep learning, machine learning. That's what people are predicting. And this would impact us in a lot of ways. Our jobs, the way we use computers, the way we use technology, it all would be affected because of the developments in this domain. So the future jobs would include solving problems, would include writing intelligent algorithms, and all the jobs which you see around, which include tedious repetitive work, would no longer exist. So this is what people predict, and is the next big. This is considered the next big thing in the technical world. But what actually is deep learning? This is what the definition I found online. It's a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain. Okay, so basically, deep learning, in deep learning, we are just trying to mimic how the human brain operates. And as you all know, human brain is one of the most powerful tools for learning. Like, it's one of the most intelligent tool we know, right? The human brain. Deep learning just tries to mimic how our brain is working. Like, how about we process the information in the same way our brain processes it? If we can process it in the same way, then it's called deep learning. This sounds really exciting. I hope you all agree to this. So, taking inspiration from the human brain gives us immense power. Machines now can be more creative and they can derive better insights. Like, there are two approach to solve a problem in programming. We have some input. We we write how it would be processed. We write the rules, we write the code, and then we get an output to it. Right? We hard code the rules to it. And the other method is when we have input and we have data and we ask machine to relate, to find the relations between it themselves and try to predict it for the newer set of data. That's what deep learning deals with, right? So it can derive those insights on its own, like we do. We create those rules, we create those relations between the data we see, the data we observe on our own. And this is what deep learning is trying to achieve. So what has made deep learning so popular in these few years is the storage cost getting cheaper. That is one factor which has made deep learning popular. For applying deep learning algorithms, we need a lot of data. We need to process humongous amount of data, which we have. If you see around us, we have smartphones, we have personal computers, we have assistants, we have so many things, and all these things are recording data. We have sensors which are recording data. So if we can use all those data to predict information, it involves deep learning. And storing all this much data, it was difficult earlier, but now it's easier. We can run a cloud machine in seconds and store all the data and then process it. So storage cost getting cheaper is one factor. The second factor is the processing power. You can see the graph, like we have already surpassed the brain power of a mouse. Our computers can now process faster than a brain of a mouse. And it is predicted that by 2023, the computing power of the machines would surpass human brain as well. So the processing power, especially by GPUs in our system, has contributed to the growth in deep learning. So how is it being used? So it is being used at a lot of places. You must have heard about how Google AI is creating more AI on its own, and how driverless cars work, and how Netflix, Amazon searches and results are so smart. They all involve some bit of intelligent learning, some bit of artificial intelligence, some bit of deep learning. So this is one application of object detection. Like, you give it an image, and it can find the object. So this is because of CNN. And there's another application, visual question answering. You give it an image and you ask some question about the image, and the computer answers that. This is actually live. You can, I think the site is this vqa.cloudcv.org. If you go to this site, you can try this thing. So there are a lot of such, I would call, cool things happening in the domain of deep learning, but they all require some more knowledge. But today we'll be just covering the basics. And once you're confident enough with the basics, um, maybe we can conduct another webinar for more topics. If you just write that in the feedback form, if you want us to conduct a follow-up webinar. So just today we'll be covering the basics. I'll now start with the theory. So after covering some theory topics, we'll write some code. We'll understand how it actually works in the code. Covering theory is important because these all topics are very basic topics. You need to know these topics before you can start writing code for it. And once you are clear with these topics, you can write more code on your own. So this is how a neuron looks. Okay, we have dendrites and we have an axon, and the cell body, that's actually a neuron. So this is a neuron, and so a neuron on its own cannot do much, but a network of neuron is what brain is, right? A brain has billions and billions of neurons all connected together, and that's what makes it so powerful. So how it works, the dendrites of one neuron are connected with the axon of another neuron. So the data is passed from the dendrites to axon, and is passed further in the network. Okay, so this is the basics of neuron. Now let's see how it would look like in the machine, right? So you can think these input values as dendrites. This is a neuron, and the output signal is the axon. So this is how a neuron would look like in a machine. We give it some input, and then it is processed by the neuron and given to the output, right? And you can have such a network of neurons to make a neural network. So this is one basic entity in a human brain, and we'll deal with neurons, okay, in deep learning. Remember, recall that we are trying to recreate how our brain works. Okay, so how it works, we get the input variables in the brain. In terms of our human body, it's all the values we get from our neighborhood, from our senses, eyes, touch, whatever we see. So those all values are input. In terms of machine, it's the data which we are providing to the algorithm. And there's a huge network of such neurons. Okay, so there's, in this image, this is the input layer, this is the hidden layer, and this is the output layer. This is the terminology. The input layer gets the input, the output layer provides the output, and the hidden layer processes it. Okay, so this is one. Yeah, so in this case, the input variable, what do we pass to the input variable? To the input variable, we pass the set the set of columns of the first row. So we need to take an example here. Let's say we are working in a bank, and the bank wants us to predict whether we should give loan to some person or not. Okay, we have a table of people. We have a lot of information. We have name, age, location. We have their salary, how much money they spend, and so we need to predict whether we should provide them loan or not. Okay, so these all variables are independent variables. Okay, so for me, the set of these variables would make a single observation for me. Okay, so a table would have a lot of observations and a lot of these variables. So in these input variables, we pass values of one observation, and the neuron processes it, and the output signal is for that observation. Okay, just remember that we need to standardize these values. What does that mean? It means that they should be at the same scale, because we have age also and we have salary also. So we need to standardize them or normalize them so that they are all on the same scale, and the neural network can process those values. We'll look at it later. Don't worry about it right now. Okay. Excuse me. And excuse me. Yeah. So the output value, it can be of three types. It can be continuous, it can be binary, or categorical. What does that mean? Let's say if you're trying to predict a price of, like we have a company and we make products, we need to predict the price of a product, like what we should keep the price of the product as. That's continuous data. That, so like example, a price. A binary data, like the example I gave you, for bank, whether we should give them the loan or not, yes or no. Okay. And categorical, this is used in, let's say you have an image and you need to find if that image is of a cat or a dog, right, or a lion. So there are three categories here, and you would get multiple output values in this case. So you can see that we had one output. So let's say if we had to find if the image is of cat, dog, or lion, we have three such output values, and there would be probability for each output cell. Like if we have a dog, the probability, if it's the images of a cat, the probability of dog might be lesser, let's say 0.2. The probability of lion might be 0.1, and the remaining 0.7 might be of cat. So we have multiple output values in that case. So these all topics which I'm covering right now, these all explain you how deep learning works, some basic concepts, how neuron works, how activation function and backpropagation would work. I'll cover those topics later. So these all topics, they sound very boring right now. Like I assure you that when I first started reading them, it was very boring, right? But just try to go through the, like just try to stay with this, and you'll realize that it all makes sense later. And these learning this topic would give you a lot of power to program things which you haven't done till now. Okay, so now there are there's something called weights. Okay, each input and neuron, the layer has some weight. Okay, the weight determines value, how much that value is contributing to the neuron, like or the that path, how much the value is being is contributing to the path. So it determines like how important that signal is. Okay, should it be passed along that or no? Like if the weight is there is 0, then that signal is not really important to us, right? We should not use that signal, right? So this is how a neuron looks like. Okay, we'll later in this webinar we'll make a network of these neurons, and weight determines how important each signal is. Okay, so when we call like training a network, I'm sure you must have heard of these terms, training a network or training a model. What that involves is finding the values of these weights. Okay, when we start, we keep some random values, we give some random values to this weight, and while training them, we try to predict the right weight values. What are the right values for these weights? Okay, I'll tell you how we do that. So this is what training a network is. We find the right weight values, we just provide them input, and we get the output for that observation. Okay, so now what happens inside a neuron? I told you that it just processes the information and provides us the output, but what actually happens inside a neuron? Okay, so you can see this. Actually, we take the summation, and inside the summation we have wi and xi. So this is called a weighted sum. Okay, xi is actually these input values. So x1 is input value 1, x2 is input value 2, and like similarly xm is input value m. Right, we multiply them with the respective weights and sum all of them. Okay, right, this is what we have here. So you observe here that we are considering all the weights and all the input values here, right? And we are summing them. Okay, then we apply an activation function, okay, to this value, and that returns us an output. Okay, activation function, another daunting term. Don't worry, like even it took me some time to understand myself. So no, yeah, even it took me some time to understand this term. So activation function is a function which takes the weighted input and provides us an output. Okay, now how this activation function works, I'll tell you right now. So, but apart from activation function, you have learned a lot till now. You know that we have input values, you know we have weights, and you know we have a neuron which uses activation function on the weighted sum and provides us an output. Simple, right? So this we have covered a lot by now, and we'll be discussing activation function in more detail now. Okay, so I'm sure you must have seen this function, the unit step function or the threshold function. For values above 0, it gives 1, and for values below 0, it gives 0, right? Simple. This is one example of an activation function. So if the weighted sum was, let's say, was somewhere here, let's say 5, then this threshold function would give you 1, and if it was, let's say, minus 0.5, so then it would be, the output would be 0 in that case. Remember, threshold function is just one type of an activation function. Okay, we have more types of activation function. We have threshold function, we have sigmoid function, and we have rectifier function. These all are types of activation function which we can use. There's one more which I haven't covered here, that's called hyperbolic tangent function. Okay, so you don't need to know these functions in detail. It's just that while making the neural network, I'll take these terms and then you might get lost. Okay, what is a sigmoid function? So just I'm covering the basics right now. It's all right if you don't know how to make these function and what these functions are doing right now. It's all right. Don't get scared with the names. Sigmoid function looks like this. Okay, we generally use this to find probability. You can see that it has continuous range of values. We use this to find probability, and we generally use it in the last layer when we have to find the probability of the output. So that's where sigmoid function is used, and this is a rectifier function. It returns x for value above 0. Okay, so this is a rectifier function, and this is one of the most important function in deep learning. This is used a lot. This is one of the most famous function. So rectifier function looks like this. Okay, and it's called ReLU. It's also known as ReLU in deep learning. When we write the code, it's called ReLU because that stands for rectifier linear unit. Okay, so which basically has this rectifier function. That's it. So we have covered 3 types of activation function, and we use those activation function at different places. We'll see those places once we start writing the code. Okay, so as I told you, rectifier function is this one, right? Also called ReLU. And the sigmoid function is this one, okay, which gives us the probability, and we use it in the output layer, the last final layer. Okay, and we'll be using the rectifier function in all the hidden layers. Okay, so I'll be using this function in the hidden layers, and for the output layer, I'll be using the sigmoid function. Okay, so now we know a lot of concepts. Let's see how the entire network would work. Okay, so you remember in school, we used to work with functions like y equal to fx. We just used to pass x to a function, and it will give you some output. Right? Hey, you can, instead of passing x, like that was just one variable, you can pass multiple variables, x1, w1, x2, w2, and so on. This should give us a output, right? We have worked with these functions, like passing multiple parameters and then getting an output. That's how our programs work, right? The power of neural networks, it lies in the hidden layers. We have an input layer, and finally we have an output layer. Okay, in between we have a lot of layers, and those layers are called hidden layers. Those layers they don't tell us the output, they don't tell us the input, right? Though the values they tell you, we cannot understand them on our own, right? But those layers are really important. The hidden layers are really important. Why? Because it considers the factors which we might miss. Okay, let's say we make a, I told you a problem earlier of if you have to find whether we can whether we should give the loan to some person, yes or no, right? This was the problem we are dealing with. So if we write some normal linear function for this, like in terms of y equal to fx, we consider all those, we consider relations, and we write a function for that, right? But the neural network would give you power to find relations which you can't even think of, which you don't even know. It finds the factors involved on its own. Like it sounds like magic, but that's how it works. It it has some layers, hidden layers, which actually find relations between the input variables and how much each variable is contributing and how should we use it. Okay, it actually finds those relations which we might miss, which we can't think of, and it provides you an output. It automatically on its own finds the weights of the signals. It automatically finds those relations for you. All you need to know is the input, and it will give you the output. Okay, and this is all based on the training data which you provided the network. Okay, so how it works is we have input, we have output, we have some hidden layers. That's how a network looks like. Okay, and we provided some training data to the input, and people get, and we know the output. Okay, so based on that training data, the network learns how to find the output on its own for future values. Okay, and then we can use that model once it's trained to find output values for some new data which the machine hasn't seen earlier. Okay, so this is how a neural networks look like. And like I've written here, like the age and location, the age and expenditure. So in the loan example, these all relations, how much they matter, it's all being predicted by the neural network on its own. Okay, so as I told you that we train the network, then we predict the value. Okay, we call the value predicted y dash. Okay, and we know the value y, the actual value y for the training data. Okay, so let's say we have 10,000 rows. We have a past history of customers for a bank. We know that this person took the loan, they paid or not, they did not pay, and this was their salary, this was their age, and so on. Right, we have past data, it's called training data. Okay, we we try to take all the input values, we take all the input values, we predict an output value and compare it with the actual value, right? So in this case, it would be, did the person pay back or no, yes or no, right? So we try to predict a value, and then we find how close are we to the actual value. Okay, so this is called cost function. A cost function tells you how close you are to the value or how far you are to the value. It's actually the error in your prediction, right? So you find a value y dash, and you know that the right value should be y, so that the gap, the difference, that's the error. Okay, and a cost function looks like this. So c is equal to 1 by 2 y dash minus y whole squared. This is one example cost function. The cost function tells us how far we are from the actual value, how much the error is. Okay, so this is how a neuron looks right now. Okay, we have input values, we have weights, we have a neuron which uses activation function. I told you, like, recall, we have different kinds of activation function. We'll be using ReLU for hidden layers and sigmoid for the output layer. We apply activation function on the weighted sum, and then we try to predict a value, right? It's called y dash. We know the actual value is y, right? And we find c, which is the cost function, the error in our prediction. Okay, so we find c, right? Now how do they learn? We know c now, right? What did I tell you? That training a neural network involves changing these weights, right? Changing the values of these weights, and the neural network knows how to find the values of these weights on its own, on its own. How would we do that? So we find the cost function, this function for each observation. Then we add the cost function for all the rows for the training data. Let's say you have 10,000 rows. You predict value for all those rows, and then you find the cost function for all those rows, right? So now you know how far you are for each actual value and for each observation, right? We have traversed through the entire data, right? And now what we'll be doing, we'll be sending this cost function, the error, again inside the network. Okay, again inside the network, and the network would fix these values, the weight values, on its own, and traverse through all those values again, all the entire data set again, and then again find the cost function, the sum of cost function, and then change the weights. Okay, I hope you are able to understand this thing. We try to find the values of these weights based on the error we are getting in our prediction, right? So if you give me some values, okay, and you know the output, okay, I you give me the input, I process the input, and I give you an output. You tell me how far or how much the error is. Based on that error, I'll change the weights for each factor, for each signal, and give you another value. And then again, I'll find the error and I'll keep repeating it till I have the right values, or almost the right values for the weights. Okay, we do this again and again, and we just minimize the error. Okay, that's what training a neural network involves. We have input values, we have weights, we have neuron, and we predict a value, we find the error, and then based on that error, we fix these weights. Okay, and we keep doing this for the entire data set for multiple times. Okay, so we have covered most of the theory. Okay, we now know how a neural network works. We know we have input layers, we know we have multiple hidden layers, we know we have output layers, we know how we find the error in our output, and then how we fix the weight in the entire network. Okay, we know that now, right? So let's let us cover some couple of more little topics, and then we'll start with the code. I promise, just a couple of more concepts. Okay, so I told you that we go back, right? Using C, we update these weights, and I told you that magically neural network knows how to update those weights and relations, right? So actually it's done by something called gradient descent. And what that is, a cost function looks like this. Okay, you can see that it's a parabola, right? We have y dash and we have a cost function, right? So let's say initially we are here, right? What we do is we find the slope and we change the value of y dash and find cost again. We find the slope and we change the value of y dash and find the cost again. And that's how we reach the minimum. This is the minimum cost function we can achieve. Okay, this is called gradient descent, when we have some parabola and we try to find the minimum cost function. So the set of values, the set of w's which give us the minimum cost function, the minimum cost function, those are the weights we want. Okay, so we find cost function, we find the weights, and we fix the weights, right? This is how we find the right values for the weights. Okay, so just remember this image. We find the cost function, we update these weights, and these weights are updated using gradient descent. This is one small problem here, that we might not get cost function like this always. So we use something called uh, stochastic gradient descent. Okay, and in case the cost function looks like this, let's say it goes down and then it goes to global minimum, and then it gets local minima here. Okay, so it's a curvy wavy function. Okay, And if we apply the same logic, let's say here, then we would reach the local minima here, okay, which is not the best result right? We know that we need to take the error here, right? And how do we do that? Okay, everybody, this is, I know you might be getting confused here. What is happening? Just try to understand that we are trying to reduce the error. That's all. That's it. All we're trying to do here is just reduce the error. Nothing else. We'll just reduce the error here. Okay. And why are we trying to reduce the error? Because the values of the weights at which the cost or the error is least, those are the values we want. That's it. That's how we are trying to reduce the error. And I told you gradient descent, it finds the minimum. It's a concept of mathematics. It finds the minimum of parabola. But if you apply gradient descent here on this graph, we reach a local minima, which is not actually the best result for the network, right? So in this case, we make huge fluctuations. Like let's say we start here, then we reach a point here, then we reach here, then we reach here, then we reach here, and then this is how we reach the global minima. We need to make bigger fluctuations, and we achieve those bigger fluctuations using stochastic gradient descent. Okay, like let's say this is the data we have, right? We have these input parameters. Let's say the age of the person, the city they are living in, and how much they're earning, and how much they're spending every month, right? We have x1, x2, x3, x4 other input values, right? We predict a value y dash, and this is what we have, y, right? So I told you that find the cost function for one observation, second observation, third observation, fourth observation, and then I told you to add all those cost functions and update the weights, right? That's what I told you. And then repeat the entire epoch again. Epoch is like traversing the entire data set. That's an epoch. So we do multiple epochs, we update the weights again, but we update the weights after we find the cost function, we find the sum of the cost function, and then we update the weights after a batch. So this is batch gradient descent. But in case of stochastic gradient descent, after every observation, we would update the weight. Okay, we would update the weights based on every cost function, a cost function for every row. This is stochastic gradient descent, right? And since it has more fluctuations, we reach the global minima here because of more fluctuations. And why more fluctuations? Because we are updating the weights after every single observation in every epoch, right? Epoch is traversing the entire data set. So because of more fluctuations, we reach the global minima. Okay, so trust me, we are done with the theory now. We know all the concepts, but this is just how a neural network looks like, right? We have few input layers, we have few output layers, and we have few hidden layers. Okay, we traverse through the network, we find the output, we find the error, and then we update the value, update the weights if we are doing stochastic gradient descent, or we just keep finding the cost, the error for each observation for the entire data set, and then update the weights. Okay, there are two ways to do that. There was one batch gradient descent, and there was stochastic gradient descent, right? So updating the weights, that's called backpropagation, because we are going back in the network and fixing the network. That's called backpropagation. Okay, it involves complex mathematics, how to update all those weights, and how each weight should be updated, and how each weight is affecting. We really don't need to go in that depth. All we know now is that we need to update the weights. Okay, so we are done with the basic theory now, and we'll summarize what we have learned. Okay, first we have the input layer, hidden layer. We have few hidden layers, and then we have an output layer. Okay, and we randomly initialize all those weights, something close to 0. Okay, and then we input data in the input layer. So remember, the input would be for one single observation, right? So if we have 10 people, on which we are training the network, we'll input values for first person and find the output for the first person. Then we'll input the values for second person and find the output for second person, and so on, right? So we input the first layer, then we move left to right. So we pass from input layer to hidden layer, and we propagate through all the neuron activations and all this. Just these are just terms, right? Activating the neuron using activation function, which we discussed. These are all terms. Don't worry. Input layer, we traverse to hidden layer, right? And then we find the output, right? That's called y dash. We compare the value which we get to the actual value which should be there, which is y, and we find the error or the cost function we discussed, right? We find the error. Now what we do, we back propagate. We update the weights based on how much they're responsible for the error, right? And there's something called learning rate, but ignore that for now. So we update all those weights based on the error we got, okay? And we just keep repeating the steps 1 to 5, right? And we update the values after each observation or after a batch of observation. Remember, we discussed batch gradient descent and stochastic gradient descent. Whether we should fix the values of weight after every observation or after the entire batch, okay? And you know what an epoch is? Epoch is when we traverse through the entire data set. Okay, so we do one epoch, we do second epoch, third epoch, and we just keep doing it, right, for some time. So this was the theory, how we do this. Now let's see some code, how we would actually do this thing. Okay, so I've shared a gist with you, right? You can find the URL in the YouTube video, and I'll explain you how we'll write this code. It's simple. Trust me, it's really simple. If you have some programming experience, it is going to be simple. And for this is actually Python language. We'll be using Python and the Keras library. And so you can try to run this code on your own. Like you can try it on your own, but I'll just explain you how it is working and how we write it. Okay, so you can use PyCharms for writing Python code, or you can use Anaconda. Anaconda is actually like it's actually a platform for working on Python. It has some applications built in, like Jupyter or Spider. So you can use Spider to write code in Python. Okay, so I'll show you the demo in Spider right now of how to write a basic artificial neural network based on what we just discussed till now. Okay, so let's see. You can open Anaconda and then open Spider, right? And this is the code we have now. And I just close it and then okay. So I've actually experimented a little bit, so that's why you are seeing these values here right now. So so this is Spider, right? And I'll be using some libraries, the NumPy library, the Pandas library, and the Keras library. You can just install these libraries on your machine. You can install Anaconda, and let's see how we'll write the code. Okay, so the code which we are going to write right now, we'll make a simple artificial neural network to predict these values. Okay, so we have a data set. I'll provide you the link to this data set if you require after the webinar. Okay, so we have a data set here. So this is for a bank. It has like 10,000 rows. And what this data set has is the surname of the person, the customer ID, the credit score, the geography, gender, age, tenure, balance, the number of products, and all these things, how much salary they have. And they find if the value 1 or 0 for exited. So that means, did the person leave the bank, yes or no? Okay, so let's say you have this data in a bank and they have appointed you to find if some customer is going to leave the bank or no. Like, so you want to predict the value for exited based on the data which they have. They have this data with them. So based on this data, you need to predict whether they would exit the bank or no. Okay, so let's try to use deep learning for this thing. You can use deep learning to do a lot of other things. Like, you can, like, people have used deep learning to write Harry Potter. People have used deep learning to create music, and people have used deep learning to do textual analysis on stock markets, on a lot of things, right? But this is a simple basic artificial neural network, right, which we'll be using right now. And maybe for those different kinds of neural networks, we can keep another webinar, or you guys can just read about those on your own. I'll just tell the names of different neural networks at the end of the webinar. Okay, so I hope you understand the problem. The problem we have is we need to find if the person is going to leave the bank, yes or no. Okay, and we have this data, right? So this is the code we have. You can read the code in the GIST, the GIST link. Okay, I'll be explaining you the code right now. Hey, so you would observe that most of the code we write in deep learning, most of it is just basic data processing. Like, the actual code for the neural network is really small, is less than 10 lines, or I would say 5 to 8 lines. That's it, the actual code for neural network. But most of the code is for data processing. Okay, so let's start. I'm importing some basic libraries here. Okay, in line 11 to 14. You can read the code in the GIST. I'll be speaking the line numbers as well if the code is not visible in the video. So in line 11 to 14, we import some basic libraries which we require. In line 17, we actually import the data set. It's called churnmodeling.csv. It's actually in the same directory here. See, you can see the churnmodeling.csv. So we are reading the data set. We are reading the CSV file, and we are actually making. So in Spider, you can, on Mac, you can just press Command Enter to run the selection of code. So we take all values, all the columns except the last column. And so I'll tell you the value of X. You can see that the value of X starts from 619 and goes to 101348 for the first row. Okay, so if you see in our table, it starts from credit score and goes till estimated salary. We are ignoring the row number, the customer ID, and the surname, because you know that a customer ID is something a bank provides, and it is not related to the person leaving the bank, right? And again, the surname also, it is not related to the fact that a person would leave the bank, right? So we start from credit score and we take the column still estimate salary. So this is, you can see I wrote 3 to 13 on line 18. I wrote 3 to 13, and we took the rows, the columns from credit score to estimated salary. That's what we took here. And I'll run this line also, the Y1. It just takes the last column, right? So Y is the value we have here, exited. Okay, now we have two variables. You can see X has the values from credit score to estimated salary, and Y has the values for last column, which is exited, right? Yeah, small y. You can see it's an array of values 1, 0, right? Now lines 22 to 29. Okay, now what are these values? So I told you that we can pass data through input layer. The hidden layers can process it, and the output layer would give you back the result, the output, right? So, but if you see the data set we have, right, it has terms like France and female, right? Spain and male. So a neural network doesn't know how to process these like terms. What is the significance of these terms? Okay, so we do something called encoding, right? Which provides numerical values to these textual terms, right? So it's very simple in Python. You import the sklearn module, you import some modules from sklearn, right? And then you prepare a label encoder, right? So I'll just run these lines. So I prepared a label encoder for the country column, France, Spain, and Germany, right? And then for the first column, I'll transform it. I'll transform the accelerator. So I'll just run it again. I'll run the line 25th, right? Now let's see what data we have, what values we have, right? If I do X, you would see that the second column now is 0, 2, 0, 0, 1, 0, something like this. It has given values to the country. Do label encoding for gender, right? And now if I print X again, you would see that we have numerical values for country and gender, right? Just remember that we are in the process of uh, fixing the data we have. Okay, that's it. We will make the neural network really soon. So once we have the right data, now we need to do one hot encoding. Now what is one hot encoding? If you see the slides, the next slide is about one hot encoding. So we have the list of countries, right? I gave it the name 0, 1, 2 something, and now I'll try to change it to this format in which the data is in form of 0 or 1. So we'll replace one column with 2, 3 columns, right? In this case we'll replace it with 3 columns right now. So for France it would be 1, 0, 0. For Germany it would be 0, 1, 0, and so on. Okay, this is one hot encoding. So that's what we'll do here. You can see right now we have 0, 2, 1, and once I run the one hot encoding code, the values would turn into this form, 1, 0, 0. You can see this. So this might be for Spain or France. So this is for France, right? So this is, we turned this data in this format. This is called one hot encoding. So actually this is important for the network because in this case it is able to relate to all those values, all those it can determine how much that country is contributing to the network, or and to the for that person. Okay, so this is what we did. We have good data now, right? We just need to do one last thing, is that we'll remove the first column. And why would we do that is because just know, like, if we remove the France column, right, we'll have the value for first data set as 0, 0, right? So if you know that the first column is for Germany and second is for Spain, you know if both the values are 0, it is, the value is obviously France. It's obviously going to be France, right? So we just remove the values because it's um, adding data. It's adding complications to our data. So we'll just replace it with just two columns. If both the values are 0, we know that the third value would be 1, right? This is what we do. It's called dummy variable trap. We just remove that value. Okay. Now in line 36, 37, 38, what we are doing is we are splitting the data set in two parts. We have one training data set and one we have test data set. Train data set we use to train the model, and test data set we test the model. We find how good the model is. We find the accuracy. Okay, so it's very simple. We use the train test split function. We do x train x test and y train y test, and we mention the test size. So as I told you, we have 10,000 rows in this data set, and 0.2 would be given to test, right? So 2,000 rows would be given to test, and 8,000 rows would be used to train the data. Okay. The line 40, 41, 42, 43, 44, these lines actually do standardization. Remember I told you that all the values, all the input values need to be on the same scale, right? So we have credit score and we have age. Okay, so this one value is 42 and one value is something in lakhs. Okay, so it creates complications for the network. How would a network understand how to take that value, right? So we do something called standardization. So this is how it looks like. You can find the standardization using this value. You get x minus mean x by standard deviation x. So sklearn has a method for that. We just use the method, right? And now our data is standardized. We have done encoding. We did one hot encoding. We have split the data set in two parts, and we have also done standardization, right? We are now good to go. We'll start writing code for neural network now. Okay, so let's start. We just import some Keras modules, some Keras libraries, and we'll make a variable classifier equals to sequential. We'll make this variable. Wait, I'll just run the code. Yeah. So what is sequential is like, because we are going to have a sequence of layers, right? We are going to have input layer, hidden layer, then an output layer. It's a sequence of layers, right? So I'll call it a sequential, right? I'll initialize the layers as sequential. We could have made it as a graph, but that's not required in this case. Okay. So now this is the most interesting part. I hope you were all waiting for this part, when we add the first layer to a network. Okay, so look at the line 61, classifier.add. This line is adding the first layer in our neural network, right? What we do is we call the add method. In Spider, if you press Command I, it gives you documentation about that method. So we are using the add method, right? And it just takes one argument, that's the layer, right? So we used the dense method to make a layer, right? I'll just show you the documentation for this. You can see, so dense layer, these are the arguments which a dense layer expects. So the first output, the first parameter is the number of output layers. So now recall, we have input layers, we have hidden layers, right? So the input would be the number of features we have, like the age, the salary, the gender, the geography, right? The number of input we have, right? That's the number of inputs to the input layer. And the output of the input layer would be the number of nodes in the hidden layer, right? So a generally, like a general value for the number of nodes in hidden layer, we generally take it like, let's take it half of the values we have as input. Okay, so we have about 11 values in the input, right? So we'll take 6 values in the hidden layer. That's the hidden layer we have after the input layer, right? So we have actually 11 features here, 1, 2, 3, and so on. So we have 11 features, and we have 6 outputs of the first layer, right? Because we have 6 nodes in the second layer. Okay, so that's why I wrote 6 here, which is the output nodes, right? Then we have kernel initializer. This method actually initializes the weights. Remember I told you that we need to randomly initialize the weights something close to 0 before we start training the network. So this uniformly initializes those weights, and we are using the ReLU activation function Recall ReLU. ReLU was a type of activation function which looks like this, the rectifier function. ReLU stands for rectifier linear unit. Okay, the ReLU function is one of the most popular function. You use it a lot, and we're using ReLU function in the first layer. Okay, and the sigmoid function was another type of activation function. We generally use it for probabilities, and we use it in the output layer generally. Okay, so we're using ReLU activation function, and we are writing that we need 11 input parameters. That's it. That's what we are doing right now. So we wrote a first, we added a first layer, right? We added first layer. Let me just run the code. Okay, yeah, we added the first layer to our network. It has 11 input and 6 output, and it is using it is a uniformly uh, providing random values to the weights, and it is using the ReLU activation function. Okay, this is the first layer, which turns out that the first input layer is actually acting as the first hidden layer also. Okay, so the next hidden layer we add, that's actually a second hidden layer in the network. Okay, so we add another layer. Now, how many outputs do we need? We need 6 outputs, and the kernel initializer is same. We are uniformly assigning the random weights, and we're using the ReLU function because it's a hidden layer. Okay, so and notice that we are not providing an input parameter. How many inputs does it need to take? Because the network by now know what's the what is the number of outputs of the previous layer. It knows that already, right? So based on the outputs of the previous layer, it automatically determines what is going to be the input of the second layer, right? So it adds another layer. It's a hidden layer. We don't need to provide the input parameters because the number of input is going to be same as the number of outputs of the previous layer. Okay, simple. So we have another hidden layer. Now we are making one output layer. So the output of this layer is going to be 1. That's why first parameter intents is 1. Same uniform uh, method for assigning random weights initially, and the activation function is sigmoid function, right? Because it's a probabilistic function, it gives us the values for the output. Okay, so we have actually created the network. We have the network ready. We have input layer, we have a second hidden layer, and then we have an output layer. The network is ready, right? But we need to compile the network, right? So we need to write one more line, which is classify.compile. Okay, and I explain you this line right now. So remember stochastic gradient descent. That's how we determine what the weights need to be in the network, right? Remember how we make one prediction and then we go back in the network and fix all those weights and make another prediction, right? So going back is called back propagation, and in during back propagation we are changing the weights based on gradient descent or stochastic gradient descent. Okay, so we are using stochastic gradient descent here, and there are a lot of algorithms which do stochastic gradient descent, and Adam is one of the most famous algorithm which does SGD or stochastic gradient descent. So I write Adam optimizer here. Okay, and the loss function, remember the how we determine the loss. So the loss function, we are just calling it we are calling the loss function right now. I call it the actually the loss function for logarithmic. It's actually a logarithmic function for finding how much the loss is, and this is used in sigmoid function in the final layer. So we can use two kinds of cross entropy methods. There's one binary and one category. So we'll be using binary here because we need to predict yes or no, whether the person would leave the bank or no. Or if we had categories, we would have used category cross entropy. And the last parameter is accuracy. Like accuracy can, I just open the documentation. So compile method you can see. So we wrote optimizer, we wrote loss, and the last method, the last parameter is metrics. We generally keep it as accuracy, which metrics determine on what basis would the values be changed. What should be the metrics? So right now we're using accuracy of the network as the metrics. Okay, so we just compile the classifier. Now all we need to do is run the network. That's it, simple, right? We have the classifier.fit function, which would run the network, which would run the code, which would run our neural network for the training set which we had, which was of 8,000 lines. Remember, we have 10,000 lines, out of which 8,000 are for training and 2,000 are for testing. So we'll test it later, but right now what we are doing is we are training the model, and this is where the training starts. This is one of the most interesting lines in this code, line number 85. Okay, so how are we doing it? We are passing x train, which is the x values for training data. We are passing y train, which is y values for training data. The third parameter is batch size. Now, I told you in gradient descent, we do in batch gradient descent, we traverse through the entire data and then we update the weights, right? And in SGD, stochastic gradient descent, we change the value, we change the weights after each observation, right? And that's why it has so many fluctuations, and that is why it gives us global minima. This is what the property of SGD was, recall it, right? So here what we are doing is we are mixing them both. We are not updating the weights after every observation, and we are not updating the weights after every epoch. Instead, we are updating the weights after a batch of 10 observations. Okay, so we have 8,000 rows in the training data set, and after every 10 observations we'll update the weights. Okay, so the batch size here is 10, and the number of epochs. How many times do you want us to go through the entire data set? The entire data set. Yeah. So going through the entire data set is one epoch. So how many epochs do you want to do it, right? So here I'm taking 10 and 10. Like you can take some values. You can now I'm pretty sure you would be wondering, how do I come up with the values? Why did I put 10 here? So it's actually I just predicted that, okay, I just thought that we should do it in batches of 10. That's it. You can change it. You can do it 20. You can do it 30. You're free to do. You keep it any value you want. What is important is that you understand what batch size is. Batch size means after how many number of observations do you want to update the weights. Okay, so an epoch, a 10 epochs are very less. Like you should have 100, 200 epochs, right? But for now I'm just have written 10 epochs because that's where it takes lesser time. So and maybe you can read about parameter tuning once the webinar is over. Maybe I can teach you that in the next session if you want. So parameter tuning actually finds the optimal values for these inputs. Okay, like batch size can be 10, can 50, epoch can be 100, 200. What is the right value, right? What is the right optimizer function, right? Which we should use. So all these values, a network can we can do parameter tuning and try all these values on the network and find the most optimal values. So you can try out more values. Right now I'm just using 10 as the batch size and 10 number of epochs. Okay, so yeah, you can see that we are training the model for 8,000 values. It's epoch 1. We have accuracy of 79%. The model is actually having an accuracy of 79% in the first go itself. Most of it's random. It's like most predictions are randomly occurring together, like coming close to the actual values. But this is how we are trained. We are training the data right now. We are training the network right now. We did 10 epochs and we got an accuracy of 83.29. Okay, so we could have done 100, like it would have gone for 100 epochs, but I just showed it for 10 epochs right now. And Now we need our model is trained. Okay, so now we need to work with the test data. Remember, we had 2000 rows as test data, है ना? So we'll find the y predicted values for that 2000 rows of the test data. Okay, I'll just run that. It is using our classifier and the predict method to work. Okay, so we have y pred. Now let's see its value. So you can see it has given us probabilities for each observation of those 2000 rows, but we cannot use them as such. So all I'm doing here is that I'm replacing those values with true or false. So if the value is above 0.5, I'll just say yes. Otherwise, I'll say no. Okay, I'll just run that. And now let's again print my print. And you can see that the data is now converted in false and true format. Okay, and this is for the last 10,000 rows. Okay, now we need to find out how good our model is. We have a prediction, we have actual values for test data. Test data is also known data. We know that data, we know the values, but we're just testing the model, how good our model is. Okay, so we do something called we make something called confusion matrix. All you need to do is just import confusion matrix from SQL metrics and then make a confusion matrix out of test and train data. Sorry, out of test data and the values which you predicted, and it would make a confusion matrix. Simple. So let's run it. Now we can see the confusion matrix. So you can see the confusion matrix. Our model actually predicted 1565 right values and 113 right values, and it was wrong for 292 plus 30 values. Okay, so this is the accuracy of our model. I mean, this is, and how did we find that? We found it using the test data. We know the values for test data as well, but we did not train the model on the test data. Test data was a test for the model, and we now know how good our model is. Now we can easily predict the values for new data. So I have an example here. You can see that if I provide all these values to it, right, then I can make a prediction. So I'm just making a prediction here for this data set and finding if the person would leave the bank, yes or no. So this is like, this is a first working neural network. We have a network. We have two hidden layers. Actually, the first, counting first layer, the first input layer also is a hidden layer. We have three layers in this: input layer, a hidden layer, and an output layer. We have three layers in this. We trained it, and we predicted. We found some predictions. Right. You can improve it. You can apply a lot of more concepts in this and get higher accuracy. You can easily get accuracy of about 98%. Currently it's 83 right now. You can get it up to 97% or so, and you can do all those things. But since this was a basic webinar, we just covered how to make a simple artificial neural network and get accuracy of 83%, predict some values. So this was the code you made. Like, we just made our first neural network. You can try the code on your own. I can provide you the Excel file which we have, and I can provide you this Excel file. You have the code on the gist here. You can install Spider, or you can install PyCharms. You can run the code. You would have to install TensorFlow and Keras, because Keras is a library for TensorFlow. It uses TensorFlow in the backend. Okay, so you can install Keras. You can try this code. If you have more questions, you can write to me. You can write them in the feedback form, and try this code on your own. And we just made a first simple neural network. So we just made a small representation of a brain using code, and I'm sure you guys can write more code. You guys can write more better algorithms and do more interesting stuff. But this was a simple neural network which we made. Okay, so that's it for today. We discussed some basic concepts. You can write to me if you have questions. If you want to discuss something, we can talk. You can add me on Facebook, LinkedIn. This is my email address, contact@vijaynandwani.me. You can uh, write to me, and there are a lot of more concepts still left. As I mentioned, one, parameter tuning. Then there is something called okay, I'll just tell you the names of more networks so that you can read about them. So there's something called CNN. Okay, CNN is actually uh, CNN is convolutional neural networks. We use CNN to work with sorry we use CNN to work with images, right, which you saw earlier. So we can make CNN, we can make RNNs, which are recurrent neural network. So there are more types of neural networks. This was a simple artificial neural network which we made right now. So there are more concepts. You can read them on your own. If you want us to conduct another webinar on those topics or create more interesting stuff, let's say um, maybe predict stock market, or maybe do something with images. We can draw images using deep learning. We can predict, like, sorry, we can detect objects in the images using deep learning. A lot of more things can be done. So read them on your own. Try to read them on your own, and please provide us feedback how useful this webinar was, and if you have some questions which you want to ask or anything. So please write to us, and you can also provide the comments for today's session in the feedback form. We'll be circulating the feedback form shortly. So that's it. We built the first neural network. We went through some basics. Go through the slides again. You have the slides. Read more about them. Google the terms. Try to understand. Okay. Maybe watch this video again. It's being recorded. Watch it again. And I hope this session was useful for you. It helped you. And that's it. Okay. This is me signing off. Okay. I hope it was useful for you. Thank you and good night. Bye.